Hello and welcome to this video on the double slit experiment and diffraction. So let's start by asking ourselves, what is diffraction? Diffraction is the spreading out of a wave when it passes through a gap or goes around an edge. As we can see here with a water wave, we have a slit here, and as the waves pass through the slit, they change their shape here. They spread out. Okay. And on the screen we get periods of high intensity here in the middle, and then lower intensity on the edge there. Diffraction is greatest when gap is approximately equal to the wavelength. Okay, here we can, this is not accurate, but when the gap here is, about the same distance as the wavelengths, then diffraction is going to be greatest. Here the gap is much smaller, so it's not very accurate. Never mind. Okay. So what would we expect to see talking about matter and waves? So if matter went through two slits, let's see here, now we've got two slits and we fire matter, like marbles, through the slits, what would we expect to see? Well, we'd expect to see two patterns where, the marbles are allowed to go through, and then we'll just see two lines. Okay, so Young's double slit experiment demonstrate that light propagates as a wave and not as a particle. So as we've just seen, if we put matter particles through two slits, we just expect to see two lines. But if we put a wave through two slits, as we see here, we don't see just two lines. We see areas of brightness and areas of darkness, and this gives us a sort of stripy pattern. And these bright parts are where the waves interfere constructively, and the dark spots are where they interfere destructively and cancel each other out. That's not what we see for matter. But for waves, we know we get this pattern. And when we shine light through it, then we also get the same pattern as we've seen with the waves. So we have to assume, therefore, that light is a wave and not a particle, and Young's double slit experiment demonstrates this. So let's dive in a bit further. Young's double slit experiment, we've got a key formula here. Lambda, wavelength, measured in meters, equals A, slit separation, and X, fringe separation, and D, which is the slit to screen distance. Okay, we might be wondering, what is fringe separation there? Fringe separation is the distance between adjacent bright spots. So if we take the center of the first bright spot to the center of the next bright spot, that is the fringe separation, which ought to be equal distances there. Okay. Anything else on here? And A is the slit separation, so the distance from the center of this slit to the center of this slit, and capital D there is the distance from the slits to the screen. Okay, let's have a look at an example here using that formula. In a double slit experiment using light from a helium neon laser, a student obtained the following results. Width of 10 fringes, 10x equals 1.5 centimeters. Separation of slits, A equals 1 millimeter, slit to screen distance, D equals 2.4 meters. As we can see here, our units are all different, aren't they? This is centimeters, this is millimeters, and this is meters. Ideally, we want them all to be in meters, but if they were all in centimeters, that could work as well, as long as the units are consistent. Here we've got centimeters, so if we times by 10 to the minus 2, then we get that in meters. Here is millimeters. If we times by 10 to the minus 3, we can get that in meters. We want to use the equation that we just saw. Lambda equals AX over D. So X, okay, so first they're calculating the fringe separation, but we want to use the equation lambda equals AX over D here. But we've only been given the width of 10 fringes, so 10x equals 1.5. So X x equals 1.5 times 10 to the minus 2 meters divided by 10, 1.5 times 10 to the minus 3. So now we know everything. We can work out the wavelength using this formula, lambda equals ax over d. So lambda equals a, which is 1 times 10 to the minus 3 meters, times by x, which is what we just worked out here, 1.5 times 10 to the minus 3 meters, divided by 2.4, which is screen to slit distance, is given here, 2.4 meters. And if we calculate that out, we get 6.3 times 10 to the minus 7. You know this is going to be correct because visible light, the wavelength of visible light is in this range here, 10 to the minus 7 meters. If it's not, then you know you need to recheck and see if you've made some mistake in your calculation. Here we got the exact answer, 6.3 times 10 to the minus 7, and we'd like to put that into nanometers. So that's just 630 nanometers, which is a nanometer is times 10 to the minus 9. Let's have a look at another example here. Pause the video and just have a go yourself. Okay, welcome back. A microwave source is directed towards a metal plate with 2 narrow vertical slits. A receiver is slowly moved along the line XY as shown in the diagram. Okay, so here we've got microwaves. We can use visible light, we can use monochromatic light. We can also use any other waves from the electromagnetic spectrum. They don't need to be visible. Here we're using microwaves, longer wavelengths and visible light. We've got a transmitter here, so the waves being transmitted or emitted are coherent. That means they're the same frequency, they got the same wavelength. That means after they go through the slits, when they interfere on this side, at any particular point, that's going to give us constant interference. These waves have a constant phase difference being from the same source. Okay, so we're going to see, rather than changing pattern on here, we're going to see a constant pattern, and we're going to see there's going to be spots of high intensity and spots of low intensity. High intensity where the waves superimpose to interfere constructively and give areas of high intensity, and then areas of low intensity where the waves have interfered destructively and cancelled each other out, and that's going to be minima. High intensity is what we call maxima. So let's have a look at the first question. A, explain why the receiver registers a series of maxima and minima. Well, we've just talked about that. After the waves transfer through these two slits, we have two wave sources which can interfere. They're of the same frequency and wavelength. We can say they're coherent. They have a constant phase difference, which means when they interfere, we're going to get constant interference. Areas of high intensity, maxima, where the waves have interfered constructively, and low intensity minima, where the waves have interfered destructively. B, the wavelength of the microwaves is 2.8 centimeters. The separation between the slits is 4 centimeters, and the receiver is at a distance of 80 centimeters from the slits. Calculate the separation between adjacent maxima. Straight away, we know we're going to have to use the equation that we just learned. Lambda equals ax over d. Also, we notice that the units here are all consistent, which is okay. As long as all our units are consistent, then we don't need to change them into meters. We're just going to get the answer is going to be in centimeters. Calculate the separation between adjacent maxima. Okay, so A is the slit separation. So here we've got lambda equals ax over d, and we just want to calculate x because we want to calculate the separation between adjacent maxima. That is x. So x equals lambda d over a. And then we're just going to plug in the numbers there. Lambda is 2.8 centimeters. D, slit to screen distance, is 80 centimeters. And A, slit separation, 4 centimeters here. Again, you have to be careful, but as long as the units are all consistent, then that's okay. So we're going to have our answer in centimeters. and the answer is x equals 56 centimeters. Okay, good. Next question, C. Describe the effect on your answer to B when I, the separation between the slits, is halved. Okay, so this is a question where we're going to want to know the relationship between describe the effect on the answer to B when the separation between the slits is halved. So separation between slits is A, and how does A relate to X? Okay, so here we've got A and X, so X is inversely proportional to A. A is inversely proportional to X, X is inversely proportional to X, so that means we double X, we half A. So if we half the separation between the slits, that's A, half A, so we're going to double X. Let's just see if we got that. Yeah. So X is inversely proportional to A, so A is halved, X is doubled. And the same thing, the distance between the slits and the receiver is doubled. Well, it's directly proportional to X, so if we double that distance, then we're going to double X. Okay, thank you.